Hello everyone. We are going to cover a number of problems on quality control lecture. Well, what we see here is an assembly which consists of three parts, as you can see, and they are all assembled together. There is a value which is assigned for the tolerance range for the overall assembly. The assembly will have a certain length of LA, and it will have a specific tolerance range. The tolerance value for this assembly is plus or minus 0.3 mm or millimeters. Now we are asked to determine the tolerances for individual components which are assembled together, and those include T1, T2, and T3. If we know the value of the tolerance of the overall assembly to be equal to 0.3, how do we decide about the tolerances of T1, T2, and T3 for the individual parts? Well, traditionally, what engineers do in the industry is to consider the worst case scenario, and that is to evenly distribute the tolerance of the assembly to the individual parts. On the basis of that, the tolerance value for the individual parts will be equal to plus or minus 0.1, and that comes to a total of, say, 0.3 in the worst case scenario. So if we make it 0.1 to each one of the individual parts, then the worst case scenario, when you add all these values to one another, it comes to a total of 0.3, and that is taking care of the overall tolerance of the assembly. Or in the other end, if these values are negative, then what will happen is that we end up in, say, minus 0.1 for each one of them, and that will result in, say, minus 0.3 in the end. So this is on the conservative side, and in the worst case scenario, we are not exceeding the specified tolerance for the given part. However, let's see if this is the right way of doing it. Let's take a look at this example here. If we have got 3 pallets, each one of the pallets has got some 20 parts as part 1, part 2, and part 3. And in the assembly, we've got to take one part from each from these pallets and put them together in order to make the assembly. So on a random basis, we may take any one of the parts from each of the pallets. Say, for example, I'm taking part number 8 from the first pallet, part number 14 from the second, and part number 4 from the third pallet. And you may have your own choice, which could be anything other than the one that I have chosen. Now, we do not have the value, we have not yet measured the say lengths of these parts as yet, and then we measure the lengths, and these are the values that we get. Well, as you can see, the ones that are shaded are the ones that I have picked. This is the one that I have picked from the first pallet. This is the one that I have taken from the second, and this is the one that I have taken from the third pallet. And as you can see, the one in the first pallet, which is part number 8, is in red. The ones that are in red are those parts that exceed the specified tolerance of plus and minus 0.1. So we should have scrapped these parts if we wanted to make use of the traditional method of tolerancing. However, we have not. And then what I need to do is just to put these tolerances to one another to see if it is within the specified tolerance of plus and minus 0.3, or if it is exceeding. So 0.173 plus 0.04 minus 0.055 comes to a total value of 0.158, And as you can see, this is well within the specified range of the tolerance for the whole assembly. So I have not scrapped part number 8 in the first pallet, and I have used it in my assembly. And in the end, I have assembled 3 parts together, and it is well within the assigned value of the tolerance for the whole assembly. What does this mean? It means that we should not have scrapped the one that we wanted to scrap on the basis of traditional tolerancing. This one should not be scrapped, and it can still be used. The net conclusion is that traditional method of tolerancing is not the best method of tolerancing, and some of the parts that could be considered as the scrap part could still be used in the assembly without any problems. Now the question is that then how do we decide about the tolerances? Well, we've got to make use of some other methods, which is making it possible for us to widen the specified values of the tolerances, and that is referred to as statistical tolerancing. Okay, now if we make use of the equation for statistical tolerancing, this equation right here, which is relating the tolerance of the assembly to the tolerances of individual parts, Pi, and in this equation, N is representing the number of parts in the assembly. For this given problem, then we realize that the tolerance of each of the individual parts should be wider than what we had already decided, and that comes to a total of 0.173. It is perfectly fine to assign the tolerance of plus and minus 0.173 instead of 0.1 that we had initially decided. And this is giving us a lot more freedom when it comes to manufacturing of the parts. So those parts that should have been scrapped, if they are out of the tolerance of 0.1, can still be used as long as they are within the range of plus and minus 0.173. Okay, moving on to the equation sheet. This is the equation sheet for this lecture. We have got a number of equations on this equation, and those include the first equation, which is giving us the value of process capability, meaning that what we are capable of making by taking into consideration the equipment and the skill level available. And this equation is equal to mu, which is representing the process mean, which is set at the nominal value of the product, as you can see here, plus and minus 3 times of sigma. What is sigma? Sigma is defined as the standard deviation for the process. There is another equation down here for computation of process capability index. Process capability index indeed is telling us where we are sitting at in the production process, and out of 1 million parts that we are producing, how many parts will be considered as scrapped on the basis of this index. There is a table that I will show you later on, which is giving us a clear picture of how PCI can be related to the number of scrapped parts in the production process. T is representing the tolerance assigned to the part or to the assembly, and sigma again is the same parameter that we had before, that is the standard deviation. Further down, we have got an equation for sigma, which is relating the standard deviation of the assembly, denoted by A, to that of standard deviation of the individual parts. In order to understand what standard deviation is, you need to refer to the lecture materials and also do some textbooks on statistics, which is properly indicating what this parameter is and what its role is. We've got another equation down here, which is relating the tolerance of the assembly to the tolerance values of individual parts. Of course, N is representing the number of parts in both of the equations on this slide. And this is the equation that we just used in the previous slide. Okay, moving on. First problem of the homework problems: a sheet metal bending operation produces bent parts with an included angle of 92.1 degrees. Included angle is this much. The process is in statistical control. What it means, again, we've got to refer to the lecture materials to realize what is meant by statistical control. And the values of included angle are normally distributed with a standard deviation. The value of standard deviation, or sigma, is given. The value of sigma is given to be equal to 0.23. And then the design specification on the angle is equal to 90 degrees plus and minus 0.2 degrees. So the tolerance value for this given problem is equal to 4 plus and minus 2, comes to a range of 4 mm. Determine the process capability. So we are after computation of PC, process capability. And then if the process could be adjusted so that its mean is equal to 90 degrees, determine the values of process capability index, or PCI. So let's do part A first. In part A of the problem, we are to compute the process capability on the basis of the included angle of 92.1 and also a tolerance range of T is equal to 4 degrees plus and minus 2 degrees, comes to a total of 4 degrees for the range of the tolerance. And then in order to do that, what we need to do is to take the equation sheet for say PC from the equation sheet, which is this equation, that is equation number say 40.1. So this is already given to us, 92.1. The value of sigma is also given up here, 0.23. So what we need to do is just to substitute these values and get the value of PC computed. If we substitute these values, then it comes to this much, and we can compute the lower and upper limits of the process capability. Taking this value of 92.1 gives us the lower limit, and adding this value to 92.1 gives us the upper limit of the process capability. So the process is capable of producing parts with an included angle within this range. Okay, in part B of the problem, what we are asked to do is just let me get rid of what we don't need anymore. If we, in this part of the problem, we've got to consider if the process mean is equal to 90 degrees and tolerance is still 4 degrees, then what would be the value of PCI, process capability index? Again, we've got to take the equation for process capability index from the equation sheet. This equation, the value of T is already at hand, and that is equal to 4 degrees. The value of sigma is already at hand, that is equal to 0.23. So if we substitute these values, then we can easily get the value of PCI, which is equal to 2.9. This much. And this is virtually, this means that virtually there is no effects. What does that mean? We need to take a look at the lecture notes. In the lecture notes, I have included a table right here, which is relating the value of PCI to the total number of parts that are scrapped in 1 million, or to the percentage of the parts that are considered to be scrapped parts. Well, for this given scenario, for this given problem, indeed, what we have is a value of 2.9 for the PCI. If we take a look at the column for PCI, this column, as the value of PCI increases, the number of parts per million that are scrapped will be lower. So this table goes up to 2.9 and up to 2, and 2.9 will be sitting somewhere here, meaning that the number of parts scrapped per 1 million will be even less than the figure that is given down here, and that is virtually 0 defective parts in a volume of production of 1 million. So as the PCI is greater, it means that we are better off with the number of scrapped parts. Okay, moving on to the next problem. This figure shows an assembly in which the critical dimension is C. Where is the critical dimension? Right here. This is the critical dimension in the assembly. Each part used in the assembly, including the base part, has a thickness of 10 mm with process capability of plus or minus 0.1. So each one of these parts here, there are 9 parts altogether, all the way, including the base part, there are 9 parts. And these ones will have a thickness of 10 mm and the process capability is plus or minus 0.1. What it means is that the thickness of each one could be something between 9.9 up to 10.1. Okay, and then the value of tolerance for this, for T plus or minus 0.1, comes to a total value of 0.2. That's what it is. 0.2. So writing with mouse is not easy. Okay, 0.2. That's the value of tolerance for each of the parts. And then given that the process capability index for the parts is equal to PCI of 1. And also the value of PCI for the whole assembly is the same value, is 1. Determine the recommended tolerance for C using A, worst case design or traditional design, and B, statistical tolerancing. Okay. First, let's see which one of the, what is the dimension C itself. Okay. From this figure, it's very obvious that the dimension C, in order to get the dimension C, we've got to take 2 thicknesses of the 5 thicknesses of the parts, which is on this side. So the main dimension of C is equal to, say, 20. And then its tolerance range has to be also computed. The tolerance will be sitting up here. You've got to have it computed as well. In the worst case scenario, let's see which one of the parts is playing a role in determination of critical dimension C. The thickness of the base part, which is sitting here, there is no role. That is, if this part is either thicker or thinner than what it is, it's not going to affect the value of C. So this one is playing practically no role in what the dimension of C is. So the dimension of C is a function of the thicknesses of the remaining 8 parts. So there are 8 parts in the assembly which are deciding the critical dimension C. And the tolerance of each one of these is plus and minus 0.1, which comes to a total of 8 times of plus and minus 0.1, or 8 times of 0.2 millimeter. So if we want to get this computed, then what we need to do is just to write down what we have. So far, this is the equation for PCI. And then this is the equation. This is the values that are given. PCI for the part and for the assembly is equal to 1. So if the value of PCI is equal to 1, what it means practically is that T is equal to 6 times of sigma on the basis of this equation up here. If PCI is 1, then T is equal to 6 times of sigma. And then, according to this, because we know that the value of T is equal to 0.2 from the statement of the problem, we can easily get the value of sigma out of this equation, and that comes to this much. So the value of sigma is now computed for individual parts. And then, as I mentioned before, the critical dimension, we've got 5 parts on the left, 3 parts on the right, and the gap between these two is 20 mm. So this is the main dimension of the critical dimension C. Now the task of us is to determine the tolerance for this critical dimension on the basis of traditional approach or the worst case scenario, and on the basis of what we have explained, tolerance of the assembly for the critical dimension is a function of tolerances of 8 parts. So 8 times of tolerances of the individual parts, which comes to 8 times of 0.2, comes to a tolerance range of 1.6 mm, and that could be written in the form of plus and minus 0.2. 8. So this is the traditional approach of determination of tolerance for the critical dimension, which is considering the worst case scenario. And in part B, we are asked to compute this on the basis of statistical tolerancing. What do we do? We've got to take a look at the equation sheet that we have, this equation sheet, and take the equation for the tolerance from the equation sheet for the equation for the statistical tolerancing. This one is from here. We know the value of Ti, which is 0.2. We know the value of N, which is 8 parts are participating in this. Then it gives us the value of the tolerance of the assembly on the basis of statistical approach. And that's what we will do. So this is the equation that we have taken. All we need to do is to substitute the values 8 times of 0.2. And then just do the computation, which is giving us this value. And we can rewrite it in this form. And as you can see, the value that is now extracted or obtained from this equation is giving us a tighter range compared to the worst case scenario or traditional approach that we had used. So if we take into consideration the statistical approach, the tolerance of the dimension C, critical dimension C, will be tighter. So it is practically giving us this, say, tolerance range instead of the one that was wider. So it is helping us. Statistical approach is always helping us in assignment of the tolerances to different parts. So we end up with a more accurate assembly if we make use of this approach. Okay, moving on. Now we are asked to solve part B of the previous problem, except that process capability index for the assembly is a more conservative value of 1.5. The PCI for individual parts still remain the same at 1. Okay, what do we do? In order to do this problem, again, we've got to take a look at the equation sheet and take the equation from the equation sheet, equation for the PCI. This is the equation for PCI. For the parts, it remains the same. However, for the whole assembly, now the value of PCI is equal to 1.5. And then this will change the right side of the equation. That is, T will be equal to 9 times of sigma instead of what we had before. So T is equal to 9 times of sigma instead of 6 times of sigma, 6 times of sigma that we had in the previous scenario when PCI was equal to 1. So we take this equation from here and then back to the statement of the problem. Okay. Now, what we have for the individual parts, PCI is equal to 1. For the individual parts, tolerance is equal to 0.2. Sigma is this much for the individual parts, and the value of C was already computed to be equal to 20. And then if we take a look at the table that I had explained before in this column, the value, if PCI is something equal to 1.5, it is sitting somewhere here, meaning that we will end up with a less number of scrapped parts compared to the situation when we had PCI equal to 1. If PCI is equal to 1, the number of scrap parts in 1 million is 2,700. For 1.5, it is less than 63 because it is sitting somewhere here. So it will be less. And then, well, we've got to just do the computation as I explained. Now TA, which is the tolerance of the assembly, will be equal to 9 times of sigma of the assembly. We don't have the sigma of assembly, but we do have the sigma of the individual parts. How can we relate this to that one? We've got to take a look at the equation sheet again. Equation sheet, and on the basis of the equation that we have got here, equation 40.st1, ST stands for the statistical tolerancing. This equation relates the say standard deviation of individual parts to the standard deviation of the whole assembly. And then back to the problem. On the basis of this equation, we can get the value of sigma A, and the value of sigma A will now sit in this equation right here, giving us the value of the tolerance of the whole assembly. And that comes to this much. And as we can see, this is now wider than the previous tolerance range in the first part, in the previous problem. It was plus and minus 0.283, which is now widened to plus and minus 0.424 mm. And because of that, the number of scrap parts will be less because now tolerance range is widened for more than what it was before. Okay, moving on to the next problem. In this problem, what we need to do is to actually construct control charts. In the lecture, we explained what are different types of control charts and how to construct them. Different steps are properly explained in the lecture notes and lecture materials. And now we are going to do a problem on the basis of lecture materials on construction of, say, control charts. Well, we have got a number of equations. Let's first read the statement of the problem, and then I will explain the equation sheet for this problem. 10 samples of size 8. N is equal to 8. We've got 10 samples, and the size of the sample is 8. Have been collected from a process in a statistical control. Refer to the lecture materials to know what is meant by statistical, about the process being in the statistical control. And the dimension of interest has been measured for each part. Determine the values of center, LCL, which is lower critical limit, and UCL, upper critical limit, for the X bar and R charts. Well, X bar, as explained in the lecture, represents the nominal dimension, the characteristic which is of interest in comparison with the nominal dimension, and R stands for range. It's telling us what is the range of error or how far that given sample is from the nominal dimension. As the value of R is less, we are doing a better job. The calculated values of X bar and R for each sample are given below, right here. So we've got the calculated values of X bar, which is the average of the 8 parts in the first sample, comes to this much. Average of the second parts comes to this part, and just like that. Okay. And in B, construct control charts and plot the sample data on the charts. Okay, what we need to do is, in the first step, we needed to compute the values of X bar and R. And this is already done in this problem. So step 1 is already done. We've got it. And in the second step of the problem, we've got to do the computation of the grand mean, or X double bar. What do? We've got to add all these values of X bar to one another. These are the averages of each sample. We've got to add them together all the way, and then divide the whole value, whatever it is, divided by the number of samples, which is 10 in this given scenario, and that gives us the grand mean, or X double bar. And similarly, we do the same for the second row, giving us the value of R bar. This is the second step. So we do it that way. For computation of grand mean or X double bar, we add all the 10 values of X bar to one another and divide it by the number of samples, giving us 9.2 as the grand mean of X. And for R bar, we get the averages of these 10 values, and that gives us an R bar of 0.24. So on the basis of this, now we can do the computation of the upper and lower boundaries. Let me just take a look at this slide here, which is telling what we are doing. This is indeed these charts belong to another problem which I had covered in the example problem. So do not worry about the values that are written here. Indeed, for construction of the X bar chart and R chart, we've got to do the computation of the center, upper critical limit, and lower critical limit. Similarly, we've got to do the computation of center for the R chart, upper critical limit, and also lower critical limit. These are the ones that we need to compute. Now let's get back to the equation sheet. We've got an equation sheet In the equation sheet, we have got two equations helping us to do the computation of LCL and UCL for the X bar chart, and also LCL and UCL for the bar chart. What do we need to consider for LCL of the X chart? We've got to get the grand mean of X, which is already computed. We've got to compute R bar, which is already computed. And also we are in need of the value of A2. The value of A2 can be taken from the table down here if we have the sample size at hand. Sample size N is equal to 8. And as it was mentioned in the statement of the problem. So we just get the values of in this row out from this table. So the value of A2 is this much, 0.373. The value of D3 is this much, and the value of D4 also that much. So we take these values from this table, which should be substituted in the above equations. For computation of LCL, we need A2. For computation of UCL, we again need A2. For computation of LCL of the R chart, we need D3. For computation of the UCL of the R chart, we need D4. All these three parameters can be taken from this table down here. Okay, so we take these values and do the computation of what is needed. So the center bar for the R chart is already computed right here. This is giving us the value of the center for the X chart. And by making use of the equations on the equation sheet, we easily compute the values of LCL and UCL for the X chart. And similarly, this is the value of say center for the R chart, and we take the equations from the equation sheet and do the computation of LCL and UCL for the R chart. Now we have done the computation of whatever is needed in part A. In part B, we need to construct control charts and plot the sample data on the charts. That is, we've got to construct an X chart where we have got the center line, upper limit, lower limit, and then we have got the values of X, 10 different values, giving us different values just like that here and there. We've got to just plot these. Here in the horizontal axis, we will have the values of, as you can see up here, we can have different values of X on the vertical axis and also sample numbers on the horizontal axis. So we have got sample, the value of sample 1 here, 2 here, just going all the way up to 10. And then we'll have a number of points here and there, and then eventually we've got to connect them to one another, connect all these points to one another. As long as it is in statistical control, it remains between the upper and lower limits. And what do we have here is the values of X, of course. Similarly, we construct this chart for our chart. So this part of the problem is left to you. So this is considered as a student problem. So you've got to do it yourself. This is a student exercise. You've got to construct charts like this. You can take a look at the example problems that we have done in the lecture room with some with the same charts that are constructed. And similarly, you've got to do this part of the problem. Okay, and that's it for today. Thank you very much for your participation.